Okay, looking at our second topic in this second half of chapter 4, we are looking at understanding and applying the compound interest formulas. Do you guys remember doing compound interest in Algebra 2? It's a yes or no question, guys. Yes. You guys remember it? Okay. And then we're going to look at how we can use our exponential growth and decay formulas to model changes in population as well. Okay, so just some applications of those formulas. At your tables, talk very quickly. What is that basic exponential growth equation? Not the complicated one that we're going to get to today, but just our basic one. When we talked about figuring out interest after 5 years, that kind of thing. Refresh your memory. All right, I heard a few people. What did we have for that basic one? A or Y, yeah, it can be either one, equals. Okay, so if you're using the real generic one, Y equals A times 1 plus R to the X. Okay, if we're talking in terms of money, what did we do? We used a P instead of the A. All right, so we had a P in place of our A for that. What did the P stand for? Principal. Yep. So we have P being the principal or the starting amount. I'm going to make this a little bigger. Maybe. That second formula in there, the compound interest one, should look familiar. Is that better? A equals P times 1 plus R over N to the N times T power. Okay. So in this formula, P still is our principal. R, what did we have R standing for? Our rate. Okay. But typically that's just given as an annual rate. And if we have compounding going on, it happens most of the time more than once a year. So the compounding idea, you're going to take that interest rate. Let's say we get 6% interest, all right? But let's say they compound it twice a year. Then that means we get 3% in the first 6 months, and then we get the next 3% in the next 6 months, all right? For a total of 6% over the whole year, but it's split. So that's why we have R divided by N. We have the interest rate, but it's being divided into those chunks. So we get a little bit in each chunk, okay? The N times T means if it's happening twice a year for 5 years, our power would be 10, right? There's 10 times that they're calculating our interest. Okay? So N is how many times it's being compounded in a year, all right? The number of compounding periods. And T was, what's T always been here? Time. All right, there's another formula. Do you guys remember a separate formula when it's compounded continuously? What was it? You remember there was one out there, but you don't remember what it is? It's the name of a shampoo. PERT, remember the PERT formula? Okay, so A equals, so final amount A equals your principal times e to the RT power. So if it says it's being compounded, You have to look very carefully. Is it being compounded continuously? If so, then you're going to use PERT. If it's being compounded not continuously, then you're going to use this one up here. Okay? All right, so let's look at our chart here. If they say it's compounded annually, how many times a year is that? Once. All right? So we have it compounding one time each year, which means the length of the compounding period is just 1 year. If they say it's compounded semi-annually, what does it mean? Yep, twice a year. So this time the length of that compounding period would be 6 months. Okay, every 6 months they would figure out how much interest they owe you. And then quarterly, 4 times a year, which means it's every 3 months. Yep. Okay, how about monthly? 12 times a year, and it's in 1 month intervals. How about weekly? How many weeks in a year? 52. So we are looking at 1 week as the length of the period. And daily, how many days in a year? 365. And so every interval would be 1 day. Okay? So when we look at that formula, they're going to say things like these words: annual, semi-annually, quarterly, right? They're going to tell you it's compounded that way. This is going to be your end value, all right? The 1, 2, 4, 12, 52, 365, that kind of thing. All right, so first example. It says your grandfather put $100 under his mattress 50 years ago. If he had invested it instead in an account that pays 3.5% interest compounded quarterly, how much would it be worth now? All right, so first thing I want you to do is write down the formula that you're going to need. Which of our formulas are we using for this? First one, second one, or the PERT one? Second one on our sheet? Okay, so let's plug in what we know. Our initial amount, our principal is $100. Okay. Now, they gave us an interest rate of 3.5%, but they're telling me it's compounded quarterly. Okay. So my 3.5%, my first thing, I have to convert it back to a decimal instead of a percent. What is it going to be? 0.035. Okay, and we're dividing it by 4, right? Compounded quarterly. Quarterly means 4 times every year. And then for my power, I need n times t. So I need 4 times, how many years did we leave it sit there? 50. So he put it under his mattress, right? So 50 years later, he still has $100 under his mattress. Okay? If he had put it in the bank instead, how much would this be worth? Grab your calculators. If you have the older calculators, you will need to put that 4 times 50 in parentheses, or just multiply it in your head and put it in as 200. All right, double check how you typed it in versus what you see on the TV here. Your calculator will divide the 0.035 by 4 before it adds the 1 to it, like it should. Okay, what do we get for a total? Did you get the same thing I did? 571? All right, since we're dealing with money, we'll round to 2 decimal places. So if he had put it in the bank instead and left it there for 50 years, he'd have an extra $471.10. Okay. All right, number 2. It says we are depositing $5,000 in a bank account that pays an annual percentage rate of 3% and compounds the interest monthly. How much money will we have after 5 years? I want you to try to just set this up. Don't type it in your calculator until you've checked with somebody else at your table. All right, so total amount that we're going to have, we put in $5,000. What do we have in parentheses? Good. Oh, sorry, by 12 you said. I wrote 4. All right, and then the power? 12 times 5? All right, and we end up with how much money? All right. So we gained an extra $808 in interest. All right. Question 3. It says you take out a $15,000 loan for your first year of college. The interest accrues during the years you are in college. If you take 4 years to complete your college degree, how much would you owe after the 4 years, and how much interest did you pay over the 4 years? In 2 different situations. So the first one, we're looking at it being compounded annually. The second one, what if they compounded quarterly? Okay. What have they not given us? They haven't given us the rate. All right, now we purposely did that because rates change. All right, so for this one, this is our current year. So anything after July 1st of 2016, we're looking at undergraduate degrees. Our interest rate is going to be about 3.76%. Okay? A few years ago when we did the same example, it was like 4.29. So they fluctuate. All right? So go ahead and use the 3.76 as your interest rate and go ahead and calculate the 2 different scenarios. All right. Do you agree with the setups that I have written there? Okay. First one, it was compounded annually, so we didn't need the big formula. However, keeping in mind that you were going to do this calculation twice, you could have put 1s in there where the ends would be so that you didn't have to retype the whole thing. Okay. So what did we get for compounding annually? $386? Point. Okay. And if it's compounded quarterly, it's still 17,000, but what's the rest of it? Okay. All right, so what does that mean? We borrowed how much? We borrowed 15,000, right, for college? And at the end of our college, 4 years later, they're going to say, okay, now you owe me 17,000 something, right? Because they're adding interest in for the 4 years that you're in school, that you're using the money. Yes? So how much of this was interest? Well, if we borrowed 15,000 and we're paying back 17,386, how much of that was interest? Yeah. $2,386.46. That's the second part of the question that they asked us. Not just what do we have to pay back, but how much of it was interest. Okay? The difference between the total you owe and what you borrowed is the extra interest they're charging. So in the second scenario, the interest was, $2,422.25. Okay? Now, that is assuming that you pay it all back when you graduate, right? Which probably isn't very likely because you're just getting out of school and you're just going to start getting a job and start making money, right? So they usually give you about a 6-month window on student loans to say you got 6 months to get a job, get your budget in order, and then you got to start paying us back. So is that the total I'm going to have to pay back? No. Those would be the totals that I have to pay back if I paid it as soon as I graduated. But if it continues to accrue interest, you're going to keep adding more money to that total bill you owe. Does that make sense? Okay. All right, question 4. It says, while in college, you become the life of the party and rack up $20,000 in credit card debt by purchasing fashionable clothing, buying meals and other things for your friends, all in the hopes of impressing the cool kids. Did I? No. No. Yeah. Okay. You have no job and you ignore the bills for 3 years. Interest on your credit card has a yearly rate of 17.94% and compounds daily. How much do you owe? Now, we've been doing a lot of interest questions, right? And we had things like 3%, right? 18% is not unreasonable for credit cards. That's very common. And it's huge. It can rack up those interest rates or rack up the total interest quite quickly. So let's look at what happens. We have $20,000 on our credit card. We are paying it back how long? 3 years later, we're going to look. We're ignoring our bill for 3 years. All right. So we have 1 plus what? What's 17.949% as a decimal? Okay, so 0.17949. It's compounded daily, which means we're going to be dividing by 365. And we said we're going to do this for 3 years, but 365 times every year for 3 years, right? All right, let's figure out what that is. So you rack up $20,000 of credit card debt. You choose not to pay anything for a while because you don't have any money. And you don't tell your parents about it, right? Because you don't want to shock them. You're going to end up paying $34,263.13, which means you're paying $14,000 some in interest. So, couple words of advice as a mother. When you go and you see something, you go, I have to have that right now. I don't have money for it, but I got this credit card. I'm going to go buy that. It's on sale right now. It's a great deal. It might not be such a great deal if you don't get it paid off right away, because then they're going to you're paying interest on it, and it's probably going to be more expensive than if you had just waited till you had the money for it. Okay? The other thing to keep in mind is when they send you the bill, it's usually every month, it's been accruing interest during that month, right? So if you put something on a credit card because they won't take, say, a personal check, you don't have your debit card, you put something on a credit card, you can go in and pay it off early, right? You don't have to wait till you get the bill. Because if you wait till they send you that bill, they've already put some interest in there. The other thing is they're going to give you a minimum payment. You got this $20,000 of debt? No problem. You only have to pay $50 this month. What a deal. It's a deal for the credit card company because they get to keep charging you interest on what you haven't paid off, right? So when you put things on a credit card, it really should be with the knowledge that I have enough money, or I'm going to have enough money in the next couple days to pay that whole bill off. All right, the longer you leave things sitting on that credit card bill, the more interest you're paying. Okay. Question 5. Once you graduate from college, you are dirt poor due to your bad credit card habits, but you have not learned your lesson. You miraculously find a job, but you can't wait for payday. You take out a $1,000 loan from one of those sleazy payday loan operations that charge 25% interest every 15 days. Now, notice it doesn't say anything about compounding in this one. It's not saying it's being compounded every 15 days. It says every 15 days they're charging you 25%. Okay, so we aren't going to actually be using our compounding formula. It's going to be slightly different. We again ignore the bills. How much would we owe in the following scenarios? What if we pay it off 1 month later, 2 months later, or after a year? Okay, so we're going to look at the 3 scenarios. We start out buying or borrowing $1,000. Okay, it's growing at a rate of 25%, 0.25. Now, here's what's different about this one. It's kind of like those half-life questions we did a couple days ago, all right, where the radioactive material decayed to half its amount in this much time. Okay, well, our interest is being calculated every 15 days. So if we wait a 30-day month, how many times have they figured out interest? Twice, right? After 15 days and at the end of 30 days. So we're going to put in 30 divided by 15 here to get that 2 to represent it's happening twice. Okay? So what do we owe in this scenario? Okay, $1,562.50. So we couldn't wait those couple days till we got our paycheck. We had to have that $1,000. So we borrowed it and then we kind of forgot. And a month later we go to pay it. We're paying an extra $562. Okay, and we only got $1,000 from them. What if we wait 2 months? What changes in our formula? Our 30 changes to 60. All right, what do we owe now? What do we got? 13,000? No, you didn't do it. Which one? Thank you. Anybody else have 2441.41? Okay. $2,441.41, and we only borrowed $1,000. So we're paying an extra $1,400 in interest. What if we wait a year? Well, how many days are there in a year? 365. Every 15 of those, they're going to charge us interest. Now what do we owe? All right. We just had to have that $1,000. A year later, we owe $228,109.65. Okay, that was a pretty expensive $1,000 we used. Okay? And you might be laughing, but it's very easy for people to get into this habit of not paying things back right away, and pretty soon you've paid a ton of money in interest that you could have used for something more fun. Okay? All right, so just to review why this one was a little different. It didn't say the 25% was an annual percent rate. Does that make sense? It just said every 15 days you have a 25% interest. Does that make sense? So we weren't dividing it by n in this case. Okay. All right. We have two more questions to look at dealing with population instead of money. It says the first mating pair of gray wolves was reintroduced into Yellowstone in 1995. The growth rate is 30% per year. What would the population be in 1995, 1998, and 2025? Okay, so the only thing that's going to change is our time. How many do we start with? 2. It's growing by 30%. So what are we going to have in parentheses? 1 plus 0.3 or just 1.3? We can put it in that way. All right. And then how about the time? If they were introduced in 1995, how many were there in 1995? Our answer should be 2, right? It said they put 2 wolves in Yellowstone in 1995. What happens here is at time 0, 1.3 to the 0 is 1, and 1 times 2 gives us the 2. So we already knew the answer to that one, right? We started with 2 wolves. Now, 1998 is how many years later? All right, so we're going to let this grow for 3 years. What do we end up with? Should be 0. And this should be 3. What do we get? 4.394. Now, does it make sense to say there's 4.394 wolves? No. So we would say there's about 4 wolves in 1998. All right. How about 2025? How many years later from 1995 is that? 30 years? All right. So what if we checked back 30 years later? Now, how many wolves are there? So 5239.99, so about 5,240. Okay. So in terms of how many decimal places to go out to, make it fit the context of the question. When we're dealing with money, we do 2 decimals. Okay. Dealing with things that can't be halves, rounded to whole numbers. All right, our last one. It says the population of ladybugs multiplies rapidly so that the population after T days is given by this formula. A of T, meaning after the total amount after T days, is equal to 3,000 times e to the 0.01 T. Okay, let's look at that. 3,000 e to the 0.01 T. It kind of looks like our PERT formula, doesn't it? Okay, so let's compare. Our initial amount is how much? 3,000. So how many ladybugs are there now? There's 3,000. Now, in terms of the growth rate, your growth rate is everything that was in parentheses. So when you think about our compound interest formulas or our exponential growth, like in the previous example, this 1.3 would be the growth rate. Okay. The only thing on the outside of the parentheses there is time. So if we look at this and say, well, P is our starting amount, T is time, this right here is like what we had in parentheses when it wasn't continuous. Okay, so our growth rate is e to the 0.01 based on this formula. What is that number? What is e to the 0.01? So we've got 1.01 and then a few more zeros. Okay, so our growth rate is about 1.01. Go ahead and set it up to figure out how much we would have after a week. What would we put in for T? T was days, right? So we're going to put in 7. Yep. So how many ladybugs are there after 7 days? Say it again. 17, 18, what would it, I don't remember what the decimal part was. Would you round up? So about 18? Okay, so about 3,218 ladybugs after a week. Questions on either population growth or compound interest? All right, we have a worksheet today again. Tomorrow will be a book assignment though, just a heads up.